All right, well, we are back once again for one of our lovely little videos, and this one is on acceleration. Now, if you remember our previous video, we were talking about velocity, and then we went into velocity that was looking at an instant, and we had this whole long discussion about what is average velocity, and it always goes back to the slope, and if you can find the slope between the 2 points, you can find it. And then you may have caught that there was like this one funky little graph where we actually looked at slopes as changing on a position time graph, and that's where we're actually at today. Okay, so we're talking about acceleration. Now, if you're looking for the kind of formal definition for what acceleration is, it's the time rate change of your velocity. In other words, you're speeding up. Okay, you're changing your speeds. That's the key thing here, is that we're changing our speeds. All right, so let's start our video today here with a little bit of a quick review. This is a position time graph, okay? So you can see that it's a position time graph, and we have a constant position through this point. We have then an increasing position here, okay? And it's increasing at a constant rate. And then we have our no change in position, then I have our decrease there. You can see that we go like that. Ideally, what I like to do is I like to always kind of convert these things or think in terms of a velocity time graph. So we'll do a little quick velocity time graph. This should go well, since we had to kind of do some matching on a velocity time graph scale this last time, or today in class. So that'll be one of those things that you'll be able to kind of look at. So again, through my first second, I'm not changing my position at all. And if I'm not changing my position, I'm not changing my velocity. And so I actually have zero velocity through that point. But then all of a sudden I go from here to here, and I see that I have a rate change of, okay, it looks like I'm up 20 for 1 second. So it's like a slope of 20 meters per second. 1 second, okay? And so I actually then go up here and I say I have a 20, and it looks like I continue on for the 3 seconds. So there's what my graph starts to look like. Then we went ahead and we said, oh, we're back to constant position. Okay, so constant position means we drop back down here, and we don't change our position for about that long. It looks like 4.5 seconds. And then all of a sudden we go from here down to here, and we say that we're going to have so now we got from point there to point there. So in 1.5 seconds, we changed our position from 60 down to 20, so it was a 40 change in 1.5 seconds. Ooh, quick, grab calculator. Clear. So 40 divided by 1.5 comes out to be like a 26, but remember that this is negative. So we end up dropping down here, over like this, okay? So we went along, we went up, we went across, we went down, and over here, over here, over here, over it, back to the beginning, okay? And that's where we stop. So that's kind of our velocity. Everything looks very square because, again, our velocities were constant through here. So this line, the slope, said that we had a velocity of that through all the points. And that's what we had for our slope on that one. So again, we're starting to equate this from position time graph into a velocity time graph. Now the other thing that you're going to notice is that we probably got through doing our little dots today in class, and our parts of our graph started to look like they curved a little bit. Okay. Now what this means is that when I was looking at this tape, you find my start point here, my dots were really, really close together. Okay. And then all of a sudden, they start to get further and further apart. So we're gapping our position as we went. So we started really close together, but then they started to get a little bit more space. So in other words, we see this increasing up here to get our position. Now, this means that our speed was changing, okay? We started at this point right here, and the slope of this line is 0. And then all of a sudden we went to a different point, and the slope started to do this to us. And we saw this increasing slope, okay? And this is something that we look at. Now this is the picture that we probably saw in another video. Now if I wanted to find the average speed, I would have just taken this point and this point, and I would have found the slope between those 2 points. That would be pretty good for my average. Now, at some point in time, the slope of this line, okay, here, let's make this better. The slope of this line is equal to a slope over here. So like maybe this line here and this line here, they have equal slopes, which means that at this point, at this instant, okay, we were traveling at the same speed as we would be on an average. That makes sense. So I'm at a stoplight, I pull away. At some point in time, I hit like 45 miles per hour, but then I get on the interstate and I'm driving like 70 miles per hour. Did I go on my average at some point? Yeah, at one point, okay? But when I get to the point over here, now the slope of this is so much greater than the average, it says that I have a greater speed. So again, I started at 0 and then I see my slope changing. As my slope changes, I get an increase in my speed. So now how does this look when we get into, say, a velocity time graph? So I'm going to do a quick little sketch here of my velocity time graph where we started at 0. Then we started to look at this and we said, well, let's start just plot our points. Okay, oops. So our velocity went from 0 and then it started to do this. So we get these points that represent a straight line, okay? And this straight line has a slope. And we want to know, what does this slope mean? Okay? This is the slope now of a velocity time graph, something in meters per second per seconds. Okay? So our slope units are going to be meters per second, or meters per second squared. That's the units that are associated with the slope of that line. Okay? So if that's true, then we should be able to start to understand what this slope really means. And it says that we now have a change in velocities over a change in time. That's how I find my slope. Let's call it something. We're going to call this acceleration. Okay? This is acceleration. It's the change in my velocities over a change in time. We'll build this into our spreadsheets with this information as well, because we'll look at that acceleration. Now, a straight line means that we have constant acceleration. Okay, it's a constant acceleration when we look at this velocity time graph. When we see this kind of a curve, we're seeing a position time graph that's not a constant velocity. Okay, it's a changing velocity. And so let's tie these all together in one kind of link here. So we have position time graphs, we have velocity time graphs, and we have acceleration time graphs. And so this is my position time graph. You can see that it's a curve. Usually follows the order of a second degree function. So something like a y equals x squared. Okay. And then this is something that looks like y equals x, okay, and I'm leaving out some coefficients, so maybe this is like an a, and we'll call this one a b, m, okay, because that's our slope one. And then this is just y equals some value, okay, and we're just going to call that some value, maybe, let's pick the letter a, okay. And what we're saying here is that we have constant acceleration, okay, it's a flat line. So this constant acceleration ties into this straight line here, which shows constant acceleration. So this graph shows constant acceleration, this graph shows constant acceleration, and this graph will show constant acceleration. So they're all showing constant acceleration. It's just that we're looking at a position time versus a velocity time versus an acceleration versus time. Now, again, math-wise, some of what we start talking about is when we talk about this in terms of functions and how we link these functions together. And I'm only going to bring this up because I know that there are some of you that are considering maybe taking the AP physics class. And if you do, we're going to try tying calculus into this. And if you're really wanting to, you could take the AP test even this year, but you have to understand the calculus points of view, which is that this function and this function are related because we're actually taking a derivative of it. And this function and this function are related because we're taking the derivative of it. We go backwards, we could find that. Now, if you remember, we found the position, okay? We found the position, or our displacement, based upon finding the area under the curve of this function to go back here, because this is v times t. We could do the same thing here. If we found the area underneath this curve, we could find our, let's see, if we call this acceleration is equal to v over t, we're actually now taking our a times t is giving us our velocity. So we're actually finding our velocity based on that. Okay? So we're finding the area based on taking the acceleration versus times our time. Okay? So that's kind of how we link these things together. It's based on either slopes, or we base it on areas. Okay, going this direction, we look at it and call that derivative. Going the other direction, we actually call that integration. Okay, so that's my calculus terms. Don't need to scare anybody off with that. Okay. When we get down to this, we start to have these sets of equations, and these are the three equations that you maybe saw on either of the boards hanging up there. These all deal with constant acceleration. Okay, so these are my constant acceleration equations. Okay, so in other words, I'm just going to back up. It's when we have graphs that look like this. Okay, we start with that graph, and then this is how we get to these equations. Now, this is my second order function here, and I'm going to write this as d equals vit plus 1/2 at squared. This should not look too scary to us, because essentially this is, or I should say, this part of this equation is the top equation that we're looking at. So if we don't have any acceleration, that's a constant velocity equation. We just tacked on this component, or this piece, this piece right here, to give us the whole concept of what happens if we're accelerating. These two equations right here are just variations of that main function. Okay, so they're just variations of that. I like, again, I have issues. Sometimes I pick up graphics to save me time for these formulas to put into my slides. This one, I do tend to use D's, and I like to use VI. VI stands for initial velocity. VF stands for a final velocity. A is always my acceleration, and T is my time. So that one does line up pretty well, but just so that you know, these are my constant acceleration equations. Okay. What I'm going to do here is I'm going to break at this point in time, and so this is the end of video 4a, okay, and we're going to let you go tonight. So if you want, you should probably go check out some of the online references that are linked to this, and then I'm going to make a video B, and video B is going to be example problems using these three equations. So you'll see some problems get worked out, because there's a good chunk of problems that deal with constant acceleration. So end of the homework for tonight. Tomorrow night, watch video B, right?